So in this video, we're going to talk about atoms. Okay, so the learning objective for this video, we're going to explain the major assumptions of the atomic theory and name and identify the properties of the subatomic particles that make up the atom. Atoms are the smallest and simplest particle of an element. It actually comes from the Greek word atomos, which means indivisible. Okay, so chemistry is built up on four fundamental assumptions about atoms and matter, which was proposed by the English scientist John Dalton in 1808. So the four assumptions that we have is that all matter is composed of atoms. So regardless of whatever substance we're talking about, everything is made up fundamentally by atoms. The second assumption is that atoms of any given element share the same chemical properties, while atoms of different elements have different properties. So what does that simply mean is that as long as you have two atoms that are fundamentally or structurally built the same, they have very similar properties. Not similar properties, they have the same properties, really. All right, so one hydrogen atom to another hydrogen atom, they're both hydrogens, so they're going to act the same. While a hydrogen atom and a carbon atom, all right, if they're structurally different, they're going to act differently. Okay, there may be some similarities. You know, they all have protons, neutrons, and electrons, and we'll kind of get to that a little bit later. But at the same time, because they structurally, the number of subatomic particles they have are different, they're going to also have different chemical and physical properties. Now, the third assumption is that chemical compounds consist of atoms combined in specific ratios. And so what do we mean by that? So if we're talking about water, right? And I mean, I'm pretty much sure all of you guys know this and heard of this. You know, water, AKA, is H2NO, okay? Water consists, or a single water compound, okay? Compounds is defined as a substance that is made up of different atoms that are chemically bonded together, okay? So when we're talking about a single water molecule or single water compound, it consists of two hydrogen atoms bonded to an oxygen atom. And water always looks like this, okay? And so you'll never find a water molecule that consists of two hydrogen atoms bonded to two oxygen atoms. That's actually a completely different substance. This is hydrogen peroxide. All right, which have completely different properties, right? You don't want to drink hydrogen peroxide, you want to drink H2O. And so when it comes to the specific ratios, all water molecules are built or made the same. Same thing as carbon dioxide, right? Carbon dioxide consists of one carbon and two oxygens bonded together. All right, and so as long as you have one carbon and two oxygens bonded together, you have carbon dioxide. Any different ratios of these atoms, you have yourself a different compound. Different compounds will have different chemical properties. Like, for example, you have carbon monoxide, one carbon and one oxygen. All right, carbon dioxide, pretty much harmless to humans. Carbon monoxide, with enough concentration, it's pretty lethal. All right, so that's the third assumption, that chemical compounds consist of atoms combined in a very specific ratios. And the last and final assumption, chemical reactions change only the way atoms are combined in compounds. The atoms themselves are unchanged and do not disappear. You know, we also call this a law of conservation of matter or mass. But the whole point is, like, for example, if you have water, let's talk about water again, right? And so the decomposition of water, you could run electricity through water and you will see that you would decompose the compound. All right. Now, from just physical observation, it just seems like everything's just disappearing. But when you look at what's going on at the microscopic level, the atomic level, really, what we see here is that you take H2O and you break them down to H2 plus O2. All right. And so the whole point of what it's saying here is that atoms are not destroyed. If anything else, you're just rearranging how they are, their structure, or how they are bonded to one another. And so, for example, if you have two molecules of H2O, what's going to happen is that at the end, when you successfully decompose this, you're going to have 2 molecules of H2. So now, instead of hydrogen being bonded to oxygen in such a way that it kind of looks like this, here's your oxygen atom, and it's bonded to 2 hydrogen atoms. All right, and so if we do this twice, so here's our 2 molecules. The blue represents the oxygen, the red represents the hydrogen. Now you're going to have hydrogen atoms bonded together. So no, they are no longer bonded to the oxygen. And then you're going to have a set of oxygen atoms bonded together as well. And so if you look at what's going on between the before and after, all right, before we always had 4 hydrogens and 2 oxygens, okay? And afterwards, you still have 4 hydrogens and 2 oxygens. So atoms are neither created or destroyed in any of these scenarios. Everything just gets rearranged. Now, when we're talking about the size of the atoms are extremely, extremely small. I mean, you're ranging, like if we're talking about the hydrogen atom, you know, it's about 7.4 times 10 to negative 11 meters in diameter. While if you're talking about the cesium atom, which is right now the biggest observable atom, natural observable atom that we know of, it's roughly about 5.24 times 10 to the negative 10 meters in diameter. All right. And in mass, atoms also vary in mass. While in hydrogen, again, you got 1.67 times 10 to the negative 24 grams. But the atom uranium, which is about the heaviest natural element that we know of, it's roughly about 3.95 times 10 to the negative 22 grams. Okay, but the whole point is that they're extremely, extremely small. Okay. Now, atoms are made up of 3 subatomic particles. Okay, we got the protons, neutrons, and your electrons. Okay. Now, the masses of atoms, as we mentioned earlier, are very, very small. And in some cases, it's very, very inconvenient. All right. How small they are. So, scientists or chemists, they express the mass of atoms and the subatomic particles really in relative mass scale. Now, the basis of this relative mass scale is of a carbon atom. Okay. So this carbon atom will consist of 6 protons plus 6 neutrons. All right. We give this atom the mass of 12 atomic mass units. All right. Or other words, you will see is written as AMU. Now, an atomic mass unit, just to kind of give you some type of comparison, an atomic mass unit, 1 AMU, is equal to 1.660539 times 10 to the negative 24 grams. So that's what 1 AMU is, okay? So to simplify things, most chemists will agree that the mass of a proton, all right, so that a mass of a proton, it's roughly about 1 AMU. And then, I mean, you could see that here. And then the mass of a neutron is 1 AMU as well, just to simplify things for the general masses. But now, one of the things that you should also notice is that the electron, it's about 1,000 times smaller than the mass of protons and neutrons. And due to the fact that electrons are just that much smaller, typically when we are calculating the masses of atoms and stuff like that, we completely ignore electrons altogether. So anytime and we'll see this in later videos, that when we're calculating masses, we never ever take account of electrons. We only look at the mass of protons and neutrons. Now, protons, they have a positive 1 charge. Okay, neutrons, they are neutral, and then electrons have a negative 1 charge. Protons and neutrons, they both are held together tightly held together in the center of the atom, which we call the nucleus. All right, so the average diameter of the nucleus is about times 10 to the negative 15 meters. And electrons, they reside around the nucleus in the area that we call the electron cloud. On average, electron cloud is about times 10 to the negative 10 meters in diameter. All right. So if you were to try to compare the size of an atom of an everyday object, so if you think about the football stadium, right, and if the atom was the size of a football stadium, then the nucleus would be the size of a pea in the center of the stadium. And so that kind of gives us an idea how much space is between the nucleus and the electrons or the electron cloud. All right. And so when we kind of think about the overall structure of the atom and what's really kind of going on, all right, the overall structure of the atom is determined by the complexities and the relationships between the attractive and the repulsive forces of these subatomic particles. So, like, what do I mean by that? Well, in the center, you have your protons. All right, so here's your proton. I'm going to say the protons, right? All right, and then in the electron cloud, you have your electrons, okay? Now, they attract one another. There is an attraction. And so due to this attraction, this is what keeps the electron in place, keeps it from, flying around just randomly, because there is an attraction between the positively charged subatomic particles and the negatively subatomic particles, the protons versus your electrons. But then at the same time, all right, in the electron cloud, you have other electrons. Oh, let me erase that. All right, so you have other electrons in the mix as well. Now, these two electrons, okay, will actually repel one another. Now, this repulsion effect will cause that the electrons will try to spread it far from each other as much as possible. But even though they are trying to repel one another, all right, so here's another set of electrons, right, they are still being attracted to the nucleus, all right, where you have your protons. And so they are spread far enough that they can stay away from each other, as for electrons, away from each other as far as they can, but then close enough to the nucleus, so because of the attractive forces of the protons. All right, and so this is what accounts to the relatively large volume that we find that the electron cloud occupies.